video, I'm going to summarize some of our conclusions when we looked at the age of a penny. Our goal was to estimate the true mean age of a penny. And we each had an opportunity to look at several pennies to get a sense for their variability and their averages. So each of us had a collection of maybe somewhere between 25 and 30 pennies. And here's one person's data. We found that the ages, here they appear to be in descending order. We had one that was 48 years old. We had, for example, two that were 44 years old. And there were some that were relatively new, so only 2 years old. And then when we calculated our statistics, our one variable statistics, we could find an average age of the penny and a standard deviation for the age of the penny. So we found that in this student's sample, we found that the average age of the penny was 22 years old. The standard deviation for the age of the penny was 16 years old. So we want to be thinking about the idea of a sampling distribution, where instead of looking at the age of individual pennies, we're looking at the averages of a sample of pennies. So if I see a sample of 22 years old for a penny, I might think about, well, what kind of variability might I see in the sample mean of repeated samples? And I might have something like this, 30, 40. Okay, so here, this was one person's sample average. We'll call that the sample mean, X bar. Another person might get an average that's higher. They might get a sample mean of, say, 27. So that would mean in their sample of pennies, they had a few pennies that were older. Somebody might have a large collection of newer pennies and estimate that the sample mean is 16. So instead of looking at the individual pennies, we're now looking at the average of a group of pennies. And in order to do this, we would have to have the samples all be about the same size. So let's say they're all 30 pennies, and these are the averages that we find. Okay, so in our lesson, we explored the behavior of this guy, this sample mean, in repeated samples. And we should know that the behavior of the sample mean in repeated samples depends a great deal on the sample size. So that's what we investigated in the applet. So let's just kind of review what we discovered. Okay, so in summary, we saw that the sampling distribution of the sample mean, X bar, will follow a normal model in certain circumstances. Always, when the population is normal, the sample mean will also be normal, but a little bit less variable. Okay, because we're averaging over several observations. So I kind of here's X to represent individual observations. Here's X bar to represent mean of samples. So N equals some sample size. Okay, and we take the averages. In another circumstance, if the original population is skewed and the sample size is large enough, and we look at the distribution of sample means, we will be able to assume that that distribution is normal only in certain circumstances. And that circumstance has kind of a rule that statisticians have decided on, where if the N sample size is greater than or equal to 30. So if you, and that's a pretty conservative choice. We tend to see a normal model even for sample sizes that are smaller than that. But to be conservative, we say that this behavior will be observed when the sample size is 30 or more. There are a couple of conditions that we have to check in order to use the methods, and those methods involve finding a standard deviation of the sample mean, right? How that sample mean varies in repeated sampling. And that calculation actually relies on independence. We can't do the mathematics behind that calculation without assuming independent observations. So we get independent observations when the data are randomly selected and when the 10% condition is satisfied. So that means that the sample must be less than 10% of the population. And a way you might see this expressed is something like this. N must be less than, just less than, 10% of the population. So we talked about that condition a little bit in class in regards to proportions, and we have to check the same condition when we're dealing with proportions, but it has to do with we want to avoid taking out too large of a subset of the population, because if we do take out too large of a subset from the population, then we can't assume independence because probabilities are changing. It would be like if I wanted to estimate the true number of, the true proportion of day students in a particular class at school. So class is maybe 100. If I take a sample of 50 and I happen to select a lot of day students in the early selections, then the probability of getting subsequent day students decreases. So that really messes up our calculations. And I know that I was talking about proportions in that case, but it's just easier to conceptualize it, but it's the same concept when we're working with means. Items have to be randomly selected so that there's no change in probability based on previous selections. So for example, if I instead of randomly selecting students from Williston's population, if I selected a friend group and I observe that the first person selected from that friend group is a day student, that's probably going to give me some information about whether the additional people in the sample are going to be day students as well. So probabilities changing because the group was not randomly selected. It wouldn't be representative of the population, and the observations would not be independent. So those things are very important to check. These are the formulas that we do need to know. They're summarized in your book. So if we're looking at a sample mean and we want to describe its distribution, there are a couple things that will always be true if the conditions are satisfied, okay? So we take a sample, we find the mean, call that x bar. The sample size is n, drawn from a large population with mean and standard deviation. Then we can say that the mean of the sampling distribution is the mean of the population. Okay, so whatever the mean of that population is, that will be right at the center of the sampling distribution. So if the true mean age of a penny, for example, is say 18, and then we take samples, those sample means will be centered around the true mean. And if the sample size is large enough, they will follow a normal model Okay, so all this is saying is that for all of these sample means, if we looked at their average, the mean of all sample means would be in the middle, would be mu, which is some claim about the population. That's not a variable, that's a known value. Okay? So that's what that statement is saying. And then the standard deviation tells me that, first of all, we notice that it's divided, we take the population standard deviation, divide it by the square root of the sample size. So if I'm given that the standard deviation of the individual ages of the pennies is something like 12, let's say, they vary by that much, and the sample size is, let's say it's 40. We looked at 40 pennies and we found that this would actually have to come from the population. We would have to know this to assume that it's true, right? Maybe somebody knows that the true mean age of a penny is 18 years and the standard deviation for the ages of pennies is 12 years. So if I wanted to know how much the sample mean will vary in repeated sampling, I'm going to use this formula. It comes from random variable transformations, and there is a mathematical derivation. If you're ever curious or ever have time to take a look at that, it's helpful to understand where that comes from. So I would take 12 and divide by my square root of 40, and I get 1.90 or so if I round. And of course we always interpret these things, so I'll write that interpretation. Okay, so we can say that on average the sample mean deviates from the true mean by 1.90, so that would be years. Okay, so notice how much smaller that variation is as compared to the standard deviation of individual pennies' ages. Okay. So that's an overview of the sampling distribution of the sample mean. And this falls into an important theorem called the Central Limit Theorem, which says that a simple random sample of size n from any population with mean mu and finite standard deviation sigma, the central limit theorem says that when n is large, and we tend to say greater than or equal to 30, the sampling distribution of the sample mean is approximately normal. Okay, here are some pictures that kind of illustrate that. So if we have a really skewed or crazy looking distribution and we take samples of 2 from that population, we still get a lot of weird behavior in the distribution. But as we increase that sample size, here n is 5, it's bigger, we still don't quite see the normal model that we're looking for. We still see a little bit of right skew, and here's some outliers, so we wouldn't apply a normal model to this one. Samples of 10, increasing the sample size, I still see a little bit of right skew. It's harder to see, but it's there. And the mean, and it's really hard to see these things, but these 2 marks right here are the mean and the median, and we can see that they're still somewhat different, so we don't quite have our normal model. But here n is 25, so that's really close to 30, our guideline. And this distribution, these are all distributions of the sample mean in repeated sampling. And this distribution really looks to be close to normal. So we can then use all of these, we can then use normal calculations, just like we did with proportions, to find things like the probability that a sample proportion or sample mean is greater than or equal to something. And then we would be using our normal CDF, and all that. So the next video is an example where we have to apply these things and do the methods to calculate such probabilities. So all these things now are probabilities for sample means. What's the probability that the average of a sample is within this range? And if we check our conditions and use our formulas, we can do that now.